Okay. Chapter 7 has 3 sections. 7.1 you should have already listened to or looked at. The next 2 sections, 7.2 and 7.3, look at specific sample proportions in 7.2, sample means in 7.3, and how we use that to do some calculations. So, 7.2, sample proportions. What are we going to do? Well, after this section, you should be able to find the mean, standard deviation of the sampling distribution of sample proportions. Check 10% condition before calculating the standard deviation and sample proportions. Determine if the sampling distribution of sample proportions is approximately normal. If appropriate, use a normal distribution to calculate probabilities involving a sample proportion. So how good is that p-cap as an estimate for the parameter p? The sampling distribution of p-cap answers this question. Consider the approximate sampling distributions generated by the simulation in which simple random samples of Reese's Pieces are drawn from a population. And we know, I guess ahead of time, we would usually, the proportion of orange candies is either 0.45 or 0.15. Okay. What do you notice about the shape, center, and spread of each? Well, let's see here. This is the 0.45 sampling. So if you have this machine and you get a bunch of these, the yellows, the orange, and the brown, then the question is, how many of these are orange, I guess? If we know the population parameter is 0.45, and we take a sample, say, of 25 of these, and we do that 400 times, then you get this distribution. And right in the middle, it looks like it's 0.45 or something very close. Okay, just suppose this population parameter is still 0.45, but we take a sample size of 50 instead of 25, and you take 400 samples just like we did before, and you plot all those, you still get this 0.45. Now these look, this is a little bit going to fool you. This goes from 0.2 to 0.7. This one goes from 0.1 to 0.8. So we've reduced this width, the spread of the data. So if we look at this now, instead it's 0.15. 25 sample size, 400 samples. We get this picture. And if we do the same thing, instead of the sample size of 25, sample size of 50, 400 samples, we know that this population is 0.15. We still get right here in the middle that 0.15 stuff. And this one looks a little nicer, a little more clear that that's the average. So what did you notice about the shape? The shape was always the same. The center was pretty dang good. And the spread of each sampling distribution, as n got larger, the spread was a little less, a little more narrow. So it can be approximated by a normal curve, if we saw that both times, that bell-shaped curve. It depends upon the sample size and the population proportion. The center, the mean, mu sub p hat, is exactly the same as that population proportion. So the average of all those p-caps is the same as the population proportion. Makes sense. Sample proportion is unbiased. The spread for a value of p, the standard deviation, sigma sub p-cap. This is the standard deviation of all those p-caps. It gets smaller as n gets larger. The value of that standard deviation for p-cap depends on both n and p. There's an important connection between the sample proportion and the number of successes. p-cap is the number of successes in the sample over the size of the sample. So it's at x over n. The mean and standard deviation of a binomial random variable, u sub x, is np, n times p. The standard deviation of a binomial random variable x, sigma sub x, is the square root of npq, q being that 1 minus p. Now, since p cap is x over n, right? P cap is x over n, which is 1 over n times x. We're just multiplying the random variable x by this 1 over n to get the random variable p cap. Therefore, mu sub p cap is this np times 1 over n, or p. P cap is unbiased. Sigma sub p cap is the sigma sub x times 1 over n. Now when we move that n underneath the square root sign, we've got to square it because it's n on the outside, but n squared on the inside. These n's now cancel, and this is pq over n. And as the sample size increases, this denominator, the spread, will decrease. So, this is just saying it again. Choose a simple random sample of size n from a population capital N with a proportion little p of successes. Let p cap be the sample proportion of successes. Then the mean is just p. The standard deviation, sigma sub p cap, is the square root of pq over n, as long as the 10% condition is satisfied. This n has got to be less than, or could be equal to, 1/10 of the population. Or 10 times n has got to be less than the population. As n increases, the sampling distribution is approximately normal. Now, you say, well, what do you mean? It increases to how much? Well, let's see. Check the normal condition by saying n times p, if it's greater than or equal to 10, or n times q, if that's greater. It's got to be both greater than or equal to 10. Then it's approximately normal, and we can use all these ideas and calculations. So if this is the population, it has some proportion p, whatever that might be, size, height, IQ, whatever. You take simple random samples of size n and get all their p caps. And then you take the average of all those. The value of all those is this normal distribution. And the average of those down the center here, the mean, is the same. So the mean of all these p caps will be p. The standard deviation square root of pq over n. The standard deviation gets smaller as the sample size increases because of that n in the denominator. So let's have an example. How we're going to use this stuff in problems. Survey of 1,012 people asked if they drink milk. They left in a bowl. This is not left by somebody else. Suppose you get your cereal and you put milk in it, and when you're done with the cereal, you have some milk left. Do you drink it? The dairy people say 70% of all adults do drink the milk. So P cap be the proportion of people who do drink the milk. What is the mean of the sampling distribution? Well, remember, the mean sub P cap is P, 70%. Find the standard deviation of the sampling distribution. Well, remember, mu sub P cap was P, but sigma sub P cap was the square root of PQ over N. So PQ is the 0.7, the Q is 1 minus 0.7 or 0.3 over N. And when you take the square root, Now, the 10% rule, 1,012, if you multiply that by 10, we get 10,120. Is that the United States number of people, United States adults? Well, I think there's more than that. So this is less than 10%. Is the sampling distribution of p-cap approximately normal? Well, let's see. N, which was, N is 1,012 times the p, 0.7. And Q is the 1,012 times the 0.3. Are those both greater than or equal to 10? Yes, they're like hundreds. So, it is approximately normal. So we have the 10% condition and the large counts is at approximately normal condition. So now we could use our information about normal distributions to help calculate things. Suppose 67% of this poll said they drink the cereal milk. What is the probability of obtaining a sample of 1,012 adults in which 67% or fewer say they drink the cereal milk? So, p-cap, approximately normal, 0.7, standard deviation, 0.0144. Can we find whether p-cap is less than 0.67? We use our technology, the normal CDF, negative infinity up to the 0.67. With the mean of 0.7 and the standard deviation 0.0144 is 0.0186. So there's a 0.0186 probability obtaining a sample in which 67% or fewer say they drink milk. This is a pretty small probability. If you put it as a percent, it's 1.86%. So there's convincing evidence against the claim. We'll talk more about what convincing evidence is later. It isn't plausible to get a sample proportion that's that small. So this is maybe too small. This is one of those samples that you picked that was really sort of out there a little bit. There will be in 2020, this year, a census because they do it every 10 years. The 2000 census, 80% of Americans over the age of 25 have earned a high school diploma. Take a random sample, 120 Americans, and record the proportion, p-cap, of the individuals in our sample that have a high school diploma. So, what are the mean and standard deviation of the sampling distribution? Well, first of all, we got to make sure that it fits. Mu sub p equals 0.80, that's 80%. Sigma sub p cap is the square root of pq over n. What is the approximate shape? Well, let's see. Is it bell-shaped? Well, we know that the 120 Americans who've taken, high school and have earned a high school diploma. That's certainly, there's more than 1,200. That's the 10% rule. The NP and the NQ will give us the bell-shaped or normal. 120 times 0.8 and 120 times 0.2 gives us these numbers all are both greater than or equal to 10. So yes, it is normal. Suppose our sample size was 30 instead of 120. Now compare the shape, center, and spread. Shape would not be normal because NQ is 6. NP is still okay. 7 times 30, 0.7 times 30 is still 21, greater than 10. The center would not change. Mu sub p is still 0.8. The spread would be larger, 0.073. Suppose you live in a small town of only 500 residents over the age of 25. What is the largest possible sample you could take? Well, let's see. The 10% rule. So the best we could do is 50. Because 10 times 50 would give me the 500. the 10% rule. There is a finite population correction that you could apply to this, but we won't worry about that in this course.